You believe space is empty because your senses have trained you to believe that nothing is what remains when everything else is taken away. You pump the air out of a container. You remove the objects inside it, and what's left feels like absence, silence, blankness. But physics doesn't care how things feel. Physics cares about what still acts, what still pushes back, what still refuses to be ignored. And here's the uncomfortable fact. Even when you remove everything you can possibly remove, space does not go quiet. It does not switch off. It does not sit there politely doing nothing. Space keeps behaving as if something is there, because something is there, and the universe keeps paying the price for it. The lie is subtle, because it's not told by teachers or textbooks. It's told by your own nervous system. Your senses evolved to survive on the surface of a planet, surrounded by air, matter, friction, and noise. They were never designed to report on reality at its most stripped-down level. So, when your brain imagines empty space, it imagines an idealized nothing, a perfect background where events happen, but which itself does not participate. Physics discovered, rather reluctantly, that this picture is wrong. Even the emptiest space we can create still has energy, still fluctuates, still affects particles, still bends the evolution of the universe. And this isn't philosophical discomfort. It's mathematical disaster. If empty space truly contained nothing, many of our equations would suddenly behave nicely. But they don't. They explode. They overshoot reality by absurd amounts. They predict a universe that should have torn itself apart long ago. That's how serious this problem is. The trouble starts the moment you ask a question that sounds innocent. What happens if you remove everything? Not almost everything. Not everything we can see, but everything. No atoms. No radiation. No heat. Classical intuition says the answer is trivial. Nothing happens, because there's nothing there to happen. Modern physics says that even in that limit, the vacuum still has a structure, still has rules, still has a measurable influence. Particles respond to it. Gravity responds to it. The expansion of the universe responds to it. And yet, we don't have a coherent explanation for why it behaves the way it does. This is where your senses quietly betray you. They tell you emptiness is simple. Physics tells you emptiness may be the most complicated thing we've ever tried to understand. The moment you accept that space itself is not just a stage, but an active participant, a terrifying implication follows. The background you assumed was neutral may be controlling the entire story. And the deeper we look, the more it becomes clear that empty space is not a harmless misunderstanding. It is one of the biggest unsolved problems in all of science. When people say empty, they are not making a scientific claim. They are describing a personal experience. Empty means no air in your lungs, no objects in your hands, no sound in your ears, no resistance when you move. It is a word built from subtraction. You remove what you can see, what you can touch, what you can breathe, and whatever remains feels like nothing at all. That definition works beautifully for daily life, because daily life never asks you to remove everything. It only asks you to remove what matters to your survival. Physics, unfortunately, asks a much more aggressive question. It asks what remains when you remove not just objects, but matter itself. And the moment you ask that question, the everyday meaning of empty collapses. Imagine you evacuate all the air from a chamber. To your senses, it feels empty. But from a physical standpoint, you have only removed molecules. The space still has electromagnetic fields, still allows light to pass, still supports forces. So you go further. You remove all particles. No electrons. No protons. No atoms at all. At this point, intuition is convinced the job is done. There is nothing left to remove. But physics is not convinced, because even now, The equations refuse to go silent. Fields remain, energy remains, and most disturbingly, effects remain. The problem is that human intuition treats emptiness as an absence of things, while physics treats reality as a system of relationships. Removing objects does not remove the structure that allowed those objects to exist in the first place. Classical physics tried to keep this distinction hidden. Space was treated as a passive container, a coordinate system where events happened, but which itself had no properties. In that picture, emptiness was simple. No matter, no problem. But even classical physics had cracks in this idea. Light could travel through empty space. Forces could act across it. Something had to define distances, durations, directions, even when nothing occupied them. Modern physics made this impossible to ignore. In quantum field theory, particles are not fundamental objects floating in space. They are excitations of fields that exist everywhere, all the time. You can remove every particle, but you cannot remove the fields without destroying the theory itself. That means the emptiest space still contains physical entities capable of storing energy and influencing outcomes. This is where the word empty becomes actively misleading. To a human, empty means inert. To physics, empty space is restless. Even in its lowest energy state, it fluctuates, not because something is wrong with our measurements, but because the structure of the theory demands it. The vacuum is not a blank page. It is a page covered in microscopic ink that never quite stops moving. Now, it's tempting to think this is just a mathematical trick, a bookkeeping artifact we could ignore if we wanted to. But nature doesn't allow that escape. The effects of the vacuum show up in real experiments. They shift energy levels. They alter forces between objects. They influence the large-scale behavior of the universe itself. You don't get to dismiss them simply because they offend intuition. The disagreement between humans and physics is not about language. It's about assumptions. Humans assume that reality disappears when objects disappear. Physics has learned, painfully, that structure remains even when content is removed. Space is not an empty box waiting to be filled. It is an active framework with its own rules. The reason this feels so wrong is because your brain evolved to ignore backgrounds. It focuses on changes, contrasts, objects, threats. The stage is invisible because, for survival, it usually doesn't matter. But the universe is under no obligation to respect what your brain finds convenient. When physicists say space is not empty, they are not being poetic. They are stating that the very thing you thought was nothing continues to participate in reality. And once you accept that, the comfortable idea of emptiness stops being a harmless shortcut and starts becoming a serious obstacle to understanding how the universe actually works. The phrase quantum vacuum sounds like a contradiction, and that is already a warning sign that your intuition is about to fail. A vacuum, in everyday language, is supposed to be the quietest possible state. Quantum theory says the opposite. The lowest energy state of a system is not calm, not frozen, and not featureless. It is active in a very precise, very constrained way. To understand why, you have to stop thinking of particles as little objects that exist on their own and start thinking in terms of fields. In modern physics, every type of particle corresponds to a field that exists everywhere in space, all the time. Electrons are excitations of the electron field. Photons are excitations of the electromagnetic field, and so on. You can remove the excitations, the particles, but you cannot remove the fields without rewriting the theory from scratch. The quantum vacuum is what you get when all these fields are in their lowest possible energy states. And that is where the trouble begins. In classical physics, the lowest energy state means nothing happens. In quantum physics, the lowest energy state still fluctuates. Not because energy is being created, but because the rules forbid perfect stillness. The uncertainty principle is not about measurement error. It is about what the universe allows to exist. If a field had exactly zero energy and exactly zero variation, it would violate those rules. So even in the vacuum, fields jitter, not violently, not randomly, but relentlessly. This is often described using the language of virtual particles, and this is where pop science usually goes off the rails. Virtual particles are not tiny objects popping in and out of existence like fireflies. They are a mathematical way of describing how fields interact at very small scales. The vacuum is not a particle soup. It is a dynamic state whose effects can be calculated and, crucially, measured. If this were just theoretical poetry, physicists would happily ignore it. But nature doesn't give that option. The quantum vacuum leaves fingerprints. It shifts the energy levels of atoms in ways that match predictions with disturbing accuracy. It produces forces between objects that should not exist if empty space were truly empty. These effects are small, but they are real, repeatable, and unavoidable. And the fact that they exist tells you something profound. Empty space has physical properties. It can store energy, it can influence motion, it can exert pressure. Once you accept that, a deeper problem appears. If the vacuum has energy, then gravity must respond to it. In general relativity, energy and mass tell spacetime how to curve. There is no exemption clause for background energy. The vacuum does not get a free pass. And when physicists calculate how much energy should be stored in the vacuum using quantum field theory, the answer is catastrophically large. Not slightly wrong, not off by a factor of 2, off by a number so enormous that writing it down feels like a joke. According to the equations, empty space should weigh so much that the universe would either curl up instantly or rip itself apart at unimaginable speed. And yet, it doesn't. The universe exists, expands slowly, and looks nothing like what those calculations predict. This is not a technical nuisance. It is a fundamental contradiction between our best theories. Quantum field theory describes particles with astonishing success. General relativity describes gravity and spacetime with equal success. But when they are both applied to the vacuum, they violently disagree. The quantum vacuum refuses to sit still, and gravity refuses to ignore it. The result is one of the most severe mismatches in the history of science. What makes this especially unsettling is that there is no obvious place to hide the mistake. The vacuum is not an exotic corner case. It is everywhere. Every cubic centimeter of space carries this problem inside it. You are not surrounded by nothing. You are immersed in a restless, structured background that modern physics does not fully understand. And the more carefully we examine this background, the clearer it becomes that the idea of empty space was never just wrong. It was dangerously incomplete the moment you accept that empty space contains energy. A consequence follows that is impossible to escape. Energy gravitates. It doesn't matter whether that energy belongs to a rock, a beam of light, or something you insist on calling nothing. In Einstein's picture of gravity, there is no distinction between respectable energy and embarrassing energy. If it exists, if it can be measured, it curves spacetime. That means the vacuum cannot be treated as a harmless background. It has weight, not metaphorical weight, gravitational weight. And once you say that sentence out loud, the universe should make you very uncomfortable. Because if empty space has weight, then space itself should dramatically affect how the universe evolves. This is not speculation. It is a direct consequence of equations that have been tested to extraordinary precision. General relativity does not ask what kind of energy you are dealing with. It only asks how much there is. And according to quantum field theory, there is an enormous amount of energy sitting in every region of empty space. You don't notice it locally because it does not clump the way matter does. But gravity does not care about clumping. It cares about totals. So physicists did what physicists always do. They calculated. They took quantum field theory seriously and asked how much energy the vacuum should contain. The answer was not subtle. It was absurd. Depending on how you perform the calculation, the predicted vacuum energy density is larger than what we observe by a factor of roughly 10 raised to the power of 120. That number is not chosen for drama. It is the result you get when you combine two extremely successful theories and let them talk to each other. And it is so wrong that calling it wrong feels inadequate. If that much energy were actually present, empty space would curve space-time so violently that the universe would not resemble anything we see. Galaxies would never form. Atoms might not survive. Time itself would behave in ways that defy recognition. The universe would either collapse into itself immediately or expand so fast that nothing could ever stick together. And yet, here we are. The night sky exists. Structure exists. Life exists. Which means something in our understanding of empty space is deeply broken. This mismatch is known as the cosmological constant problem, and calling it a problem is an act of professional understatement. It is widely regarded as the worst theoretical prediction in the history of physics. Not because it is a little off, but because it is catastrophically, humiliatingly off. When physicists talk about fine-tuning problems, this is the one that keeps them awake at night. The terrifying part is not just the size of the discrepancy, but the lack of a clear escape. You cannot simply declare that vacuum energy does not gravitate, because experiments say energy always gravitates. You cannot say quantum field theory is wrong in ordinary situations, because it works too well to discard. You cannot say general relativity fails on large scales, because it has passed every test we can throw at it. So you are left with a universe that behaves as if empty space has a tiny amount of weight, just enough to gently accelerate cosmic expansion, while your theories insist it should have an absurdly large one. Observations tell us that empty space does have an effect on the expansion of the universe, something we attribute to dark energy. But dark energy, as a label, is not an explanation. It is a confession of ignorance wrapped in a respectable name. All we really know is that space itself seems to be doing something gravitationally, and we do not understand why it is doing so little compared to what our equations demand. This should terrify you because it means the background you assumed was passive is quietly controlling the fate of the cosmos. The expansion rate of the universe, the formation of galaxies, the ultimate future of everything you care about, all of it depends on the properties of empty space. And those properties are not derived from first principles we trust. They are inferred, patched, and constrained by observation. In other words, we are flying blind through one of the most fundamental aspects of reality. What makes this especially disturbing is that the vacuum does not announce itself loudly. It does not push objects around in obvious ways. It acts uniformly, subtly, everywhere at once. That makes it easy to ignore and dangerously tempting to dismiss as a technical detail. But gravity does not ignore uniform backgrounds. In general relativity, even a perfectly smooth energy density changes the geometry of spacetime. Empty space, by simply existing, dictates how distances grow and how time unfolds on the largest scales imaginable. This flips intuition on its head. You are taught to think of matter as the main actor and space as the stage. In reality, the stage is exerting force on the actors, shaping the entire performance, and no one fully understands why. The fear here is not emotional, it is intellectual. If we do not understand why the vacuum weighs what it does, we do not fully understand why the universe looks the way it does instead of some radically different way. And worse, we do not know whether our ignorance is hiding a deeper principle or a catastrophic flaw. Empty space having weight is not a curious side effect of advanced theory. It is a flashing warning sign that our picture of reality is incomplete at a foundational level. The most unsettling possibility is that the universe is delicately balanced on something we do not yet comprehend, and that what we casually call nothing is quietly holding everything together. It is tempting to treat the problem of empty space as an abstract oddity, the kind of thing physicists argue about while the rest of the universe carries on just fine. That reaction is understandable, and it is completely wrong. This is not a curiosity tucked away in the corner of theoretical physics. It is a structural failure at the center of our understanding of reality. The crisis comes from the fact that the vacuum is not optional. You cannot avoid it by choosing a different experiment or focusing on a different scale. The vacuum is everywhere, which means any inconsistency in how we describe it contaminates everything else. Quantum field theory and general relativity are the two most successful frameworks we have ever built. One describes the behavior of particles and forces with astonishing precision. The other describes gravity, space-time, and the large-scale structure of the universe with equal authority. Each works beautifully in its own domain. The crisis appears when they are both asked the same simple question: what is empty space? They give answers that cannot both be right. Quantum field theory insists that the vacuum is full of energy, and not a little bit. General relativity insists that any energy, no matter how uniform, must curve space-time. Combine those statements honestly, and the universe should look nothing like it does. This is not a technical mismatch you can hide behind complicated mathematics. It is a direct clash between principles we rely on every day. When a bridge collapses, you do not say the problem is interesting. You say the design failed. In physics, we have learned to tolerate contradictions longer than we should because the pieces work so well in isolation. But the vacuum does not allow isolation. It sits at the intersection of quantum theory, gravity, and cosmology. That makes it a stress test for the entire framework. If the framework breaks there, it breaks everywhere. Another reason this is a crisis is that it undermines our confidence in extrapolation. Much of physics works by taking laws tested in one regime and extending them to others. We do this constantly, and most of the time it works. The vacuum problem is a warning that this strategy may fail at a fundamental level. The equations that describe particles in laboratories and the equations that describe space-time on cosmic scales cannot simply be layered on top of each other. Something essential is missing, and we do not know what it is. That uncertainty infects every attempt to understand the early universe, the origin of cosmic structure, and the ultimate fate of everything. This is not philosophical anxiety. It is practical. Models of inflation, dark energy, and cosmic expansion all rest on assumptions about vacuum energy. When those assumptions are not grounded in a deeper theory, the models become fragile. They can fit data, but they do not explain it. That is the difference between description and understanding, and physics aims for the latter. There is also a deeper conceptual crisis hiding underneath the technical one. Our language, and even our mathematics, may be built on an outdated notion of background. We talk as if space is something that exists independently of the physics happening within it. But the vacuum problem suggests that space itself is part of the dynamics, not a passive container. If that is true, then many of our standard tools are misapplied from the start. We may be asking the right questions in the wrong way. The danger of treating this as a curiosity is complacency. As long as the universe does not visibly misbehave, it is easy to postpone the discomfort. But history suggests that unresolved foundational problems do not stay politely contained. They eventually force change. The crisis is not that we lack answers. Physics has always lacked answers. The crisis is that our best answers contradict each other in a place they cannot avoid meeting. Empty space is not an exotic edge case. It is the default state of the universe. If we do not understand that state, then we do not fully understand anything built on top of it. And that is why this problem is not a footnote. It is a fault line running straight through modern physics. Common sense was never designed to survive contact with fundamental physics. It evolved to help you throw rocks, avoid predators, and not walk into traffic. So, when physics tells you that space itself is something, your brain immediately rebels. Something, in ordinary language, is an object. It has edges, a location, a texture. Space has none of those. You cannot point to it, pick it up, or remove it from the room. So common sense retreats to a safer idea. Space is nothing, a background, an absence that allows real things to exist. The trouble is that this idea quietly smuggles in assumptions that physics cannot tolerate. The moment space begins to act, influence, store energy, or affect motion, it stops behaving like nothing. But calling it something feels equally wrong, because it does not behave like the somethings you know. This is where intuition breaks down completely. The first instinctive mistake is to imagine space as a kind of invisible substance, like a thin fluid filling the universe. That picture is comforting because it turns the abstract into something familiar. But it is also dangerously misleading. Space is not a material medium you can move through or push against in the ordinary sense. There is no absolute rest frame hiding in the background. Experiments have ruled that out with brutal clarity. So common sense swings the other way and insists space must be nothing after all. Physics refuses both options. Space is not a substance, but it is not an absence either. It is a system with properties, rules, and dynamics that do not fit into everyday categories. This is unsettling because human reasoning depends on categories. We are uncomfortable with things that fall between them. The idea that space can stretch, carry energy, fluctuate, and influence gravity without being a thing in the usual sense feels like cheating. It feels as if physics is changing the rules mid-game. But it is not the rules that are changing. It is the domain. Common sense assumes a clear separation between stage and actors. Objects do things. The stage merely exists. Modern physics erases that separation. In general relativity, space-time responds to energy and momentum. It bends, stretches, and evolves. In quantum theory, the vacuum has structure and activity even in the absence of particles. The background is no longer neutral, and once the background participates, the logic you rely on starts to fail. Another way common sense breaks is through the idea of causation. We expect causes to be localized. This thing pushes that thing, and an effect follows. But vacuum energy acts everywhere at once, uniformly, without a local trigger you can point to. It does not behave like a force applied at a point. It changes the global behavior of the universe simply by being present. That violates the mental model you use to understand how influences work. You want a mechanism you can visualize. Physics offers you equations instead. Language also betrays us here. Words like empty, nothing, and background are not neutral. They carry philosophical baggage that shapes expectations before any equations appear. When physicists say space has energy, it sounds mystical or sloppy, as if meaning has been abandoned. In reality, the sloppiness lies in the everyday words, not in the physics. We are trying to describe a structure that does not map cleanly onto human experience. The result is confusion that feels emotional as much as intellectual. The final blow to common sense is the realization that space does not merely host reality. It helps determine what reality is allowed to do, the rate at which the universe expands, the way light travels over vast distances, the fate of cosmic structures. All of these depend on the properties of space itself. That turns emptiness into a controlling factor rather than a neutral absence. Common sense wants the universe to be built out of things. Physics is telling us that relationships, structures, and backgrounds matter just as much. Space being something breaks common sense because common sense insists on a world made of objects. The universe, it seems, is not obligated to honor that preference. Physics earns its authority not by claiming certainty, but by knowing precisely where certainty ends. That distinction matters here because the problem of empty space attracts confident-sounding statements that go far beyond what the evidence supports. So it is worth being painfully clear about what physicists actually know, what they infer, and what remains unresolved. We know, with experimental backing, that quantum fields exist and that their lowest energy states are not inert. The effects associated with the vacuum are not hypothetical. They shift measurable quantities in atoms, influence forces between objects, and appear consistently in high-precision experiments. These are not speculative interpretations. They are results that survive repeated testing. We also know that general relativity treats energy as a source of gravity without exception. This is not an assumption added for convenience. It is a core principle that has been confirmed by observations ranging from planetary motion to gravitational waves. When energy is present, space-time responds. That much is solid. We also know that the universe is expanding in a way that suggests empty space has a small but non-zero influence on cosmic dynamics. Observations of distant galaxies and the large-scale structure of the cosmos are consistent with a uniform energy density associated with space itself. That influence is weak, but it is real. Where certainty ends is in the explanation. We do not know why the vacuum energy predicted by quantum field theory does not show up gravitationally in the way the equations naively demand. We do not know whether the enormous theoretical value is being cancelled by some deeper mechanism, forbidden by a principle we have not yet discovered, or rendered irrelevant by a framework we do not yet possess. We do not know whether our way of calculating vacuum energy is fundamentally misguided or merely incomplete. And we do not know how to combine quantum theory and gravity into a single coherent description that treats the vacuum consistently. These are not minor gaps. They are missing foundations. There are ideas on the table, of course, symmetries, modified gravity, new fields, and known cancellations. All of these have been explored. None has emerged as a decisive solution supported by independent evidence. Some approaches work mathematically, but lack experimental grounding. Others fit observations but feel artificially tuned. This is an uncomfortable position for a field that prides itself on predictive power. Physicists are also honest about what the vacuum is not. It is not a reservoir of free energy waiting to be tapped. It is not a source of exotic particles appearing at will. It is not evidence that nothingness creates something in a philosophical sense. Those interpretations go beyond what the theory says and into metaphor that, while tempting, is misleading. The vacuum has structure, but that structure is constrained and subtle. Another important limit is linguistic. When physicists say the vacuum has energy, they are using a technical term defined within a specific mathematical framework. That statement does not imply that space is filled with hidden matter or that emptiness is an illusion in the everyday sense. Confusion rises when precise technical claims are translated into ordinary language without their boundaries. Good physics demands resisting that temptation. Perhaps the most honest thing physicists know is that the vacuum problem is pointing at something deep. It is not an isolated glitch that will disappear with better calculations. It has survived decades of scrutiny and resisted straightforward fixes. That persistence is often a sign that a conceptual shift is required, not just more precision. History suggests that when physics encounters contradictions of this magnitude, the resolution does not come from patching the old picture, but from replacing it with a new one that makes the old questions look slightly misguided. What that picture will be is still unknown. So the honest state of knowledge is this: we understand the vacuum well enough to measure its effects, but not well enough to explain its role in the universe. We can describe what empty space does, but not why it does it. That is not a failure of science. It is an accurate map of the frontier. Pretending otherwise would be the real dishonesty. The most uncomfortable part of all this is not that empty space behaves strangely. It's that, after everything we've learned, we still don't know why it behaves the way it does. You started with a simple belief. Space is just where things happen. By now, that belief should feel fragile. Space is not a passive backdrop. It has structure, energy, and influence, and those features quietly shape the universe on the largest scales imaginable. And yet, when we try to explain them using our best ideas, the explanations refuse to line up. This is not the kind of ignorance that comes from lack of effort. It is the kind that appears when you push a successful theory past the limits it was built to handle. The unsettling lesson is that understanding more does not always make reality feel simpler. Sometimes it does the opposite. The closer physics looks at emptiness, the less empty it becomes, and the harder it is to say what is fundamental and what is emergent. The vacuum sits at the intersection of quantum theory and gravity, two frameworks that work extraordinarily well on their own and stumble when forced to cooperate. That tells us something important. The universe is not obligated to be conceptually neat. It does not care that we want a clean separation between space and the things inside it. It does not care that our language treats nothing as a special case. Reality simply behaves the way it does, and our job is to keep up as honestly as we can. There is a temptation to end with reassurance, to say that this mystery will surely be solved and that everything will eventually make sense. That may be true, but it misses the deeper point. The value of physics is not in pretending confusion doesn't exist, but in confronting it directly. The vacuum problem reminds us that even the most familiar concepts can hide profound uncertainty. You live your entire life surrounded by empty space, assuming it is the simplest part of the universe. In fact, it may be the most subtle. That realization should not be discouraging. It should be grounding. It means that the universe still has the power to surprise us, not through spectacle, but through quiet resistance to our expectations. We are not living in a universe we have finished understanding. We are living in one that continues to push back when we think we have it neatly categorized. And perhaps the most honest position is to accept that not knowing is not a temporary failure, but an accurate description of where we stand. Empty space is not nothing. It is a reminder that reality is deeper than our intuition, and that the work of understanding it is far from over.